Now, we can now define power. So, now let us expand this definition of power a little bit, and we can define power in the alpha beta variables in a slightly different way. Okay. We will see how we will expand the definition of power. So, we now define something called as instantaneous complex power. Okay. So, here you see the power which we have conventionally known, it is kind of like we say P equal to V RMS I RMS cos phi, okay, 3 times, but these are all phasor quantities at steady state. Here we are talking about instantaneous quantities, these are all instantaneous variables. So, therefore, we have to kind of like expand the definition of power. So, that is why we are defining a term called as instantaneous complex power. We had earlier said instantaneous real power P 3 phase T, which we had shown in the last slide. P 3 phase T is the instantaneous 3 phase power. So, similarly, we are defining here instantaneous complex power, and how are we defining it? S t is 3 by 2 V alpha beta 0 t into I alpha beta 0 t star. Okay. As per our convention, we always say that the power is 3 times, from the conventional definition of power, 3 times V I star. Okay. And why do we do that star? We do the star because we take the reactive power flowing to an inductive load to be positive. Okay. So, we do it like this way, we put the V here, and for an inductive load the current is lagging, and so we put I star here, so that this V I star, these projections are positive for an inductive load. So, the Q is positive for the inductive load, and Q is negative for the capacitive load. Okay. That is why we use the star concept. So, here S t is also 3 by 2 V alpha beta 0 t I alpha beta 0 t star. So, suppose the 0 sequence current is not flowing. So, we will say that S t is 3 by 2 V alpha beta t I alpha beta t star. 3 by 2 factor comes because we want to keep the power same in both the alpha beta and the ABC. So, then we expand the alpha beta, V alpha beta t is V alpha plus j V beta, and I alpha beta star is I alpha minus j I beta, right, and then we multiply both of them. Then we say that this is V alpha I alpha plus V beta I beta plus j times 3 by 2 V beta I alpha minus V alpha I beta. So, there are two terms like V alpha I alpha and V beta I beta, they are the projection on the same axis, whereas V beta and I alpha is the product of two variables which are orthogonal. Okay. V beta, beta axis, and I alpha is on the alpha axis. So, therefore, we can write this as S t as P t plus j Q t, okay, instantaneous real power, and Q t is the instantaneous imaginary power or instantaneous reactive power, okay, and this is something which we will explain a little bit more. So, S t is P t plus j Q t. Okay. So, what is P t? P t, you can take the real component and then it will become this one, which is same as P 3 phase T. Okay. So, this is something which we have understood, which we know that okay, there is an instantaneous 3 phase power which is flowing from the source to the load. it is because of the instantaneous flow of energy from the source to the load. The term Qt as is shown here is something because of this cross terms like V beta I alpha minus V alpha I beta, 90-degree orthogonal terms. So, you can write it in the matrix form again, something like this, which is shown here. Okay. Now, ST, PT and QT. So, ST is called instantaneous complex power, PT is called instantaneous real power, and QT is called instantaneous reactive power. Okay. Now, this instantaneous real power in the alpha beta frame, this is what we are finding out. Instantaneous real power in the alpha beta frame is the same as the instantaneous 3-phase real power flowing in the ABC system, but this Qt is something which is a new quantity. Okay. Now, why are we defining this Qt as a new quantity? Yeah, because basically the traditional definition of reactive power is historically being developed for steady state balanced conditions. But here we are talking about instantaneous quantities which may be balanced, which may be unbalanced, which may even have harmonics. So, that definition of Q, that is capital Q, that definition of Q needs to be expanded, and that is why we are introducing this new quantity Qt, which is the sum of product of two quantities orthogonal to each other. Okay. So, this Qt, which is called the instantaneous reactive power in the alpha beta frame, this was introduced. Actually, there was a lot of there has been a lot of development of how to define reactive power, suppose on an instant to instant basis. Real power is something which is easy to understand. However, reactive power is something which is difficult, because it is traditionally it is defined as something like a power which flows back and forth between source and load. However, this definition is, there has been lot of debate on what is exactly reactive power on an instantaneous basis. Even that debate still goes on. Okay. How do you exactly define the reactive power in presence of unbalance, in presence of harmonics, etc. And one of the definitions that I am following in this course is based on this paper by Professor Akagi and his team, and this is this instantaneous reactive power, which is defined as something like this. Okay. So, those who are interested, I will suggest that you go through many articles and books for alternate definitions of reactive power. For example, you can have reactive power in instantaneous symmetrical components. Okay. So, this definition of reactive power is quite like many people use different definitions of reactive power, and we will not go into that much details here. Okay. So, probably a course on power quality or something similar like that, that may actually help us to understand this all these definitions in its full form. In this course, we will restrict ourselves to this particular definition, okay, which I am following from Professor Akagi's paper and his subsequent his team's development. So, this is the Qt. Okay. So, what does this Qt means, this instantaneous imaginary power? Okay. So, if you see here, if you write Qt, it will be something like this, okay, V beta I alpha minus V alpha I beta, and then you substitute back the alpha beta to ABC, and what do you get? You get something like this. This is very interesting actually. Okay. So, it shows that the instantaneous reactive power is basically an interaction of line voltages with the line current of the other phase. So, you see here it is the interaction of VAB times IC and the interaction of VBC times IA and the interaction of VCA times IB. Okay. So, because there is, so if you take a 3-phase system, as you can see here in this diagram, the instantaneous active power is flowing from the source to the load, but this instantaneous reactive power, it is because of the interaction of the line voltages with the line current. It is here, it is always existing because of the interaction of the line voltages and the line current in the other phase. It exists on the lines. Okay. It does not contribute to the energy transfer from the source to the load, but it exists on the lines. Okay. So, it is because of the voltage and the current interaction. So, this is the physical, to some extent the physical meaning of what is this instantaneous reactive power. Okay. So, if I substitute back, okay, what is PT, we will see 3 Vrms Irms cos phi, and Qt is minus 3 Vrms Irms sin phi. Minus sign is coming because we have taken a capacitive load, and we know that capacitive load gives positive reactive power. So, that is why the minus sign is coming here by convention, from our convention. But you see, for a balanced case, for a balanced load at steady state, Qt is exactly equal to Q, the conventional definition of power for a balanced case, okay, at steady state. Now, so if I can summarize, the instantaneous active power is equal to the conventional active power under balance case. The instantaneous reactive power is numerically equal to the conventional reactive power under balance case, but they have physical different meaning. Okay. So, conventional reactive power, how do we define? It is defined something like this, that okay, you have a voltage waveform and you have a current waveform, right, this is current and that is voltage. So, how do you define the power? So, therefore, you will have something like double frequency, this is the PT. So, the average part of this PT, the average of this PT we say the active power, whereas the oscillating part, which is this one, this we say as Q. And so, we define Q as a component of this instantaneous power. Okay. We define Q something like that, that is the oscillating part which has a 0 value, 0 average value, whereas the average value of PT is equal to P, that is the net energy flow. Now, this definition of capital Q, okay, is based on that Q, capital Q is part of the PT, okay, it is an instantaneous active, it is a component of the instantaneous active power whose average value is 0. But the definition of Qt which we have used and which we will subsequently use, this definition of Qt, which is V beta I alpha minus V alpha I beta, that definition is an instantaneous quantity. It does not flow from the source to load, it is basically an interaction between the voltage and the current. Okay. I will stop here for this Q, definition of Q here, and I will ask students who want to explore this Q cross product of these two quantities. I will ask them to explore through many articles, and in fact, there is a lot of also debate, and there are basically schools of thought of how you can define reactive power instant by instant, and how do you define it in case of an unbalanced system, in case of a harmonics, etc. But for this course I will stop here, and I will say that Qt is this definition. Qt is 3 by 2 V beta I alpha minus V alpha I beta. Okay. This is the instantaneous reactive power, which under balanced case the value is numerically equal to capital Q. We will start with, so we have, so let us then summarize what we learnt in ABC to alpha beta or through Clark's transformation. We first understood the ABC to alpha beta transformation, the mathematics of it, the matrix, how do we represent it in a matrix format, and then we also tried to understand or visualize how the ABC plane is there, and then there is an alpha beta plane. We usually make it coincident, they come over each other, and there is a perpendicular 0 axis. So, that is the visualization part. So, in case of an unbalanced system, you have you have alpha beta and 0. So, the space vector is rotating in a 3 dimensional space. Okay. And we also defined the powers. So, Pt and Qt, which are instantaneous active power and instantaneous reactive power. Okay. So, now we go to the second part of the lecture, and this is the Parkes transformation. What is the Parkes transformation? Now, we have seen that we have we have this space vector here, okay, which we are observing. We can observe from the ABC axis frame, or we can observe from the alpha beta 0 frame. Okay. So, when we observe it from alpha beta 0, when we say that this is I alpha beta 0, so this is IR. So, we say that this is I. Okay, I. So, when we observe from the alpha beta, we say I alpha beta 0. Okay. And when we observe from the ABC, we say it I ABC, okay, the same space vector. So, and the 0 vector is like on the 0 vector is perpendicular to this plane. Now, what if there is another axis which is somewhere else, okay, which is somewhere else, not coincident. So, alpha axis is coinciding with the A axis. What if there is an axis which does not coincide with the alpha axis, and what if this axis is rotating, this is not fixed. So far we have taken two axes, one is the ABC axis or ABC reference frame, which is stationary. Okay. You have A axis, B axis, C axis, these are all stationary axes, and the space vector is rotating. We have taken the second one, which is the alpha beta 0 reference frame, and there we see that alpha axis, beta axis and 0 axis are stationary. Now, we are saying that think of another reference frame, and this reference frame does not necessarily coincide with the alpha axis, and most importantly this reference frame is rotating. Okay. This is rotating, it is not stationary. So, then what will happen, or how will I visualize the space vector? If I sit on this rotating reference frame, if I sit on that rotating reference frame, how will I observe the reference vector which is also rotating? Okay. How will I see that? And this is the topic of, or this we can analyze through this something called as Dq0 reference frame. Okay. This is what we will analyze. Now, what is this Dq0 reference frame? So, as I told you that we suppose we have a reference or IT. Okay. This is the space vector. Okay. This space vector is rotating at a certain speed. The alpha axis is stationary, it is fixed. The beta axis is fixed. Now, we are introducing another reference frame which we give the name d axis, q axis, and of course, there is a 0. Okay. This 0 is perpendicular to the paper. Okay. This 0 is perpendicular to this screen on which I am recording. So, this d axis and q axis, but the point here is this d axis and q axis are not stationary, they are rotating, and they may rotate at a different speed than the rotating space vector. Okay. So, you can, how do you visualize this? You visualize this like there is a space vector so this is a space in which the space vector is there. Okay. It is rotating at a certain speed, and there is another set of axis d, q and 0, and that is rotating at another speed. Okay. Now, so if you are an observer, if you are standing on the alpha axis, okay, then what will you see? How will you observe the reference vector? So, suppose this angle is theta and this angle is theta 1. Okay. Theta and theta 1, these two are time varying. Okay. D axis is rotating at a certain speed and the space vector is rotating at a certain speed. So, let us take a condition, let us make it a little bit simplified and let us make it same for the time being. Okay. Let us make that the d axis and the space vector are rotating at the same speed. Somehow we have made it some way. Then immediately you can understand that if there is a space vector and the d axis is also rotating at the same speed, then with respect to that d axis, that space vector will become stationary, right. You can understand that if two persons are running at the same speed, then these two persons relative to each other, they will feel as if they are stationary. If they are running at a different speed, then they will see a relative velocity between them. So, that is the condition when omega dash is not equal to omega. So, if d axis is rotating at the same speed as the space vector, then they will appear to be stationary. So, okay. Now, if you are an observer standing on this alpha axis, what will you see? This I alpha beta 0. So, I t, the space vector, now if you see from I alpha beta 0, it has a magnitude, okay, and this is the angle. Okay. Any vector has a magnitude as an angle. So, this is the representation of the I vector, I t vector, if you are on the alpha beta 0. Now, if you are on the d axis, suppose you are an observer here, you are moving at omega speed, okay. You are also moving and the space vector is also moving. Okay. So, then I dq0, so you are observing the space vector with respect to your axis, that is dq0 axis, then what will you see? You will see the space vector having the same amplitude, but now e to the power j theta 1, because this angle here is e to the power j theta 1. So, you will observe this space vector standing here on the d axis, that it is e to the power j theta 1. So, substituting this I alpha beta 0 t is nothing but I alpha beta 0 t, the vector thing, e to the power minus j theta 1 plus theta. Okay. So, you substitute here and then simplify, and you will get I dq0 is I alpha beta 0 into e to the power minus j theta t. So, whatever space vector you were observing in the alpha beta 0 from the alpha beta reference frame, the space vector that you were observing, if you multiply by e to the power minus j theta, then you get the space vector magnitude and angle observed from the dq0 reference frame. Okay. Note that this theta t is not a constant value, it is varying value. So, I dq0, so what does this mean? This means that suppose I am observing a space vector from I alpha beta, from the alpha beta 0 plane, then I get a certain value I alpha beta 0 t. This is a magnitude and angle is there. And then if I want to observe the same reference vector from the dq0 axis, then I will multiply with e to the power minus j theta, where theta is the angle between alpha and the d axis. Okay. So, then I can transfer this same reference vector from one reference frame to the other reference frame. For example, I dq0 t is e to the power minus j theta t I alpha beta, and conversely I alpha beta 0 is e to the power j theta I dq0. So, here theta, what is theta? Theta is this angle here, and theta or d theta dt is nothing but omega. Omega is the speed at which the d axis is rotating. Okay. So, this is your space vector here. Okay. As I told you, the d axis may rotate at the same speed as this, or omega dash may be or may not be equal to omega. So, although this dq0 reference frame, this reference frame, again how do you visualize it? So, this is the alpha beta 0 plane and dq plane is there on this same. So, we can superimpose the dq0 plane here where the 0 is something like this, but the whole dq system is actually rotating. The whole dq0 reference frame is rotating and we are observing the space vector. Okay. The whole thing, whole dq0 is rotating, whereas alpha beta reference frame is stationary on this plane. For grid connected applications, okay, this speed, so omega of the d axis or the q axis, so d and q both are rotating at omega speed. So, for grid connected application, we generally set omega equal to the angular velocity of the fundamental component of grid voltage and current. So, for example, this is the grid current or this is the grid voltage. Okay. The velocity at which this is rotating, for example, this is equal to 2 pi into f, or it is rotating at f, where f is equal to 50 hertz. So, this may be rotating at 2 pi 50 314 or 50 hertz. So, it may be rotating there at that speed, and the d axis is also, we set that also rotating at the same speed, that is 50 hertz. So, if this grid vector is observed from the d axis when they are moving at the same speed, this will become a constant value. This will also become a constant value and it has this projection. Okay. So, this is the IGD, I grid D component, and this is the I grid Q component. When they are perfectly at the same speed rotating. And how do I get that speed? We get that speed through PLL, we will discuss it later. To how do you know at what speed the grid space vectors are rotating. However, so this is for the grid connected applications. Usually it is omega is set at the same speed as the fundamental component of grid voltage or current. But for electrical machines, okay, we can set that omega differently. We can set, for example, for induction machines, we can set it equal to the rotor speed. Okay. We can set omega equal to omega rotor. We can set the speed of the d axis as the omega of the flux, say stator flux or rotor flux or magnetizing flux. So, these are different. So, rotor speed is slightly less than the rotor flux. So, in field oriented control with rotor flux orientation, you can set the d axis same as the rotor flux at the same speed as the rotor flux, but the rotor speed may be a little bit different. It is slightly less than the flux. So, in case of electrical machine analysis, this d axis may be rotating at a different speed than the synchronous speed. Okay. So, these possibilities exist. You can see PC Cross book, okay, the I think analysis of electrical machines and drives, PC Cross. There is an extensive analysis on what happens with different speeds of this d and q axis if it is rotating at different speed than the space vector. Of course, there will be a differential speed, that is what is understood, there will be a differential speed. So, we will not go into that, we will keep ourselves a little bit simplified and we will say that this omega is rotating at the same speed as the speed of the space vector. Okay. Now, we see we can do the little bit of mathematics. We have seen I dq0 t is e to the power minus j times I alpha beta 0. Okay. They are in you can transform from one quantity to another. So, if you can expand this equation 6, we see I d plus j I q as cos theta minus j sin theta I alpha plus j I beta. Okay. So, in matrix form this can be written as something like this. So, this matrix basically transfers. So, there was one matrix before and now this matrix will help you to transfer from alpha beta 0 plane to dq0 plane. In fact, the total matrix is this one including the 0 sequence component. Okay. This matrix here, this one, this will transfer I alpha beta 0, the variables in alpha beta 0 plane to dq0 plane, and this is the Parkes transformation matrix. So, Tp, this is the Parkes transformation. Okay. I dq0, it is converts from alpha beta to dq. Okay. This is the Tp. Similarly, you can have the inverse Parkes transformation. This is Tp inverse, and that is equal to, you can just do the matrix operation and it is like this. Okay. Tp inverse. So, you can go from alpha beta to dq or dq to alpha beta. In a similar way, you can now combine the Clark and Parkes transformation by seeing that I dq0 is equal to Tp times I alpha beta, and I alpha beta is nothing but Tc times I abc. Okay. So, if you multiply this Tp and Tc, the Parkes transformation and Clark's transformation together, then you get this quantity here, which can directly convert this I abc into I dq0. Okay. So, this is direct abc to dq0 transformation. Okay. So, similar to the alpha beta thing, we can also define the power. So, the instantaneous active power in dq frame is 3 by 2 VDID plus VQIQ, and the instantaneous reactive power in the dq frame is 3 by 2, again the cross terms, VQID minus VDIQ. Okay. So, these two equations we will use for vector control strategy, okay, for grid connected as well as motor control. So, we will talk about the grid connected systems. So, with these equations in the dq domain, this Pt and Qt, we will use this, okay, the instantaneous active power and the instantaneous reactive power.